Hey there, Cool Fire crew. Welcome back to another episode of Cool Fire News, Weekly Edition, the show that brings you up to speed with the latest in tech, innovation, and everything that powers the future. I'm Siri, and today we're venturing into one of the coolest fields in engineering, robot dynamics. From robotic arms in factories to humanoid bots like Boston Dynamics Atlas, it all comes down to one question: how do robots move? And how do we control that movement? Let's unlock the secrets of robot dynamics, the science that makes machines move. Let's start with the basics. What is robot dynamics? In simple terms, robot dynamics is the study of how forces and torques cause motion in robotic systems. It helps us understand the relationship between the input, like a motor torque, and the resulting motion, like a rotating joint or a moving end effector. If robot kinematics is about motion without considering forces, like where a robotic hand should go, then dynamics is about how we get it there, accounting for mass, inertia, acceleration, and external forces. Robot dynamics is what separates a clunky machine from a smooth, responsive one. So why does it matter? Without a strong foundation in dynamics, we can't accurately control robotic arms in manufacturing, design stable walking robots or drones, simulate robots in real-time environments like video games or autonomous vehicles, or create lifelike motion in humanoid robots or exoskeletons. Bottom line, if a robot moves, dynamics are involved. Now let's break down the two main types of robot dynamics. 1. Forward dynamics. This answers the question: given a set of forces or torques, what will the robot do? In other words, if I apply this much torque to the motor, how fast will the joint move? We use this to simulate motion and predict behavior. It's especially useful in animation, simulation, and testing. 2. Inverse dynamics. This is the opposite. It answers, if I want the robot to move in a certain way, what forces or torques do I need to apply? This is the basis for most robot motion control algorithms, figuring out how to drive actuators to achieve desired motion. To better understand this, let's imagine a two-link robotic arm, like a shoulder and elbow. Each link has mass, and each joint has torque applied. When one link moves, it affects the other. This is where things get tricky, and where robot dynamics comes in. We need to consider link masses and lengths, center of mass, inertia tensors, gravity and external forces, joint positions, velocities and accelerations. This leads us to something called the equations of motion, often derived using methods like Newton-Euler, force-based, Lagrangian mechanics, energy-based. These equations let us simulate how a robot will respond to inputs, or figure out how to apply the right inputs to get the movement we want. Let's talk real-world application. Imagine you're building a robotic arm for pick-and-place tasks in a warehouse. You need the robot to move fast, but also smoothly and without overshooting. You can't just tell it, move your hand here. You need to calculate how much torque the shoulder and elbow motors must apply to get there on time, considering the weight of the object it's carrying and how fast it's accelerating. If you ignore dynamics, the robot might shake or vibrate, miss the target, overload its motors, or even break itself. This is why dynamics is essential to safe, accurate robot control. Let's zoom out and talk about some important terms in robot dynamics. Degrees of freedom, DOF. The number of independent movements a robot can make. A 6-DOF arm can move in 3D space with full orientation. Jacobian matrix, a fancy mathematical tool that relates joint velocities to end effector velocities, super useful for velocity and force analysis. Inertia matrix describes how the robot's mass is distributed and how it resists motion. This shows up in all motion equations. Coriolis and centrifugal forces. When robots move fast, especially rotating arms, these forces can affect stability. You've got to compensate for them in your control algorithms. Now let's take a quick breather and see if you're following along with a little quiz time. Question 1. What does forward dynamics calculate? A. Required torque for a movement. B. Resulting motion from applied force. C. Robot velocity given its position. Answer B. Forward dynamics tells us how a robot will move based on the forces applied. Question 2. Which of the following is not a force the robot must consider in its dynamics? A. Gravity. B. Friction. C. Font size. Answer C. Unless the robot is editing documents. Question 3. What kind of dynamics do we use to control a robot's movement? A. Reverse. B. Inverse. C. Passive. Answer B. Inverse dynamics lets us compute the torque needed to follow a planned motion path. So what's next after mastering the fundamentals? If you're diving deeper into robot dynamics, here are a few advanced topics worth exploring. Trajectory planning with dynamic constraints, dynamic control, PID, computed torque control, and model predictive control, MPC. Dynamic simulation tools like Gazebo, ROS, PyBullet, and VREP. Collision handling and real-time adaptive control in uncertain environments, force feedback, and haptics in human-robot interaction. These are the skills that separate a basic robot from a high-performance, real-world-ready system. Let's wrap this up with a real-world example. Take a quadruped robot. Like a robotic dog, it needs to move quickly and stably across uneven terrain. Every step it takes must consider ground reaction forces, shifting center of mass, coordinated joint torques across multiple legs, and real-time feedback for balance. This is robot dynamics in action, allowing a machine to move with grace, speed, and stability. So whether you're building an industrial robot, an autonomous drone, or just simulating motion in a video game, robot dynamics is what makes your machine move like a pro. That's a wrap for this week's episode of Cool Fire News, Weekly Edition. We explored the basics of robot dynamics, from forces and torques to real-world applications and control strategies. Hopefully, you now see the beauty behind a robot's motion and the math that makes it work. Next week, we'll take a closer look at AI and robotics, how intelligence and motion come together to create autonomous machines that can think, learn, and adapt. Make sure to follow and share this episode with your fellow tech enthusiasts. And as always, stay cool, stay curious, and never stop building.